Question 1. We're told, as the parachutist jumps, the initial speed is 0. We're told that she falls for 3 seconds, and we're told that the acceleration is 10. So using v equals u plus at and just substituting in, we get a velocity of 30 meters per second. So for part B, we've got to sketch a speed time graph for the motion of the parachutist. So velocity and time. And then, so we know for the first three seconds we are constantly accelerating until we get to a velocity of 30. That's from part A. And we're now told that we decelerate for 2 seconds. So we decelerate for 2 seconds. So that's us decelerating there. And then we're told that we then got a constant speed until she reaches the ground with that constant speed. So at this point in the question, we've got our 30, we've got our 3, and we've got our 5. We don't work out the 6 and the t until a bit later. Now for part C, we've got to find to the nearest whole number the value of t. So this time here. Now we know that the area under a velocity time graph is the distance travelled, and we're told that that's 550. So we're going to need to work out the value of t such that the area under this is exactly 550. So first thing we need to know this point here. So let's just work out this speed. So just considering this journey here, we know our initial speed was 30. We know we're decelerating at 12, so our acceleration is minus 12. And the time we were doing this for is 2 seconds. So using v equals u plus at again, we can see that our value for v will be 6. So now I'm going to work out the area under here, breaking it down into 3 shapes. So I've got a triangle, then a trapezium, then a rectangle. So the area of the triangle is half times 3 times 30. The area of a trapezium, remember you average the parallel sides and multiply by the depth. So that length is 30, that length is 6. So averaging those and multiplying by 2, I get the 36. And then the area of this rectangle is base, which is t minus 5 times 6. So adding those 3 together, that total area being the distance is 550. So working this through, t is my only unknown, so I can work out that t is 83 seconds. Now part D, we're now told that the model includes the effect of air resistance. Well, think about it, if you're parachuting and you're taking into account the air resistance, it's going to take you longer to get to the ground, so the new value of t would be greater. And then part E suggests one further refinement to the model apart from air resistance to make the model more realistic. So I've just copied and pasted this straight out of the mark scheme. So you could allow for the effect of wind, or allow for the dimensions of the parachute and spin, use the more accurate value of g, or allow that the parachute doesn't fall exactly vertically. Any of those would do. So question 2, now it's crucial to get the diagram right, so let's just focus on this for a bit. Okay, it's a light inextensible string. This string is taut, so start off by getting these 2 equal and opposite tensions in here. Okay, so that arrowhead is pointing towards the pulley, that arrowhead is pointing upwards. Okay, they cancel out overall, but when you're going to look at P and Q individually, they're a component in the forces. Now it's inextensible, so whatever acceleration that Q is doing as it goes downwards, P is going to be having the same acceleration going left to right. We're told it is a smooth horizontal table, so there's no friction to consider, up here. And obviously there's the weight force here, so just make sure you have an arrow going downwards, the weight of this being 0.6 g. Now, part A, show that the acceleration of Q is 4.2. So we're going to look at Q and P individually, and I think it's really important that you understand this rather than just try and sort of learn exactly which way around it goes. So we're looking at Q, we're going to be resolving in the direction of motion, which is downwards, it's moving downwards. Now we're going to use F equals ma. So think about the left hand side first of all. What is the net force? What forces have we got going on? Well, we've got the weight of Q, so 0.6 G going downwards, and we've got the tension going upwards. Now, because we're moving downwards, this one must be the biggest force. This has got to be bigger than T. So the net force is going to be 0.6 G take away T. So that's our net force, and that equals its mass of 0.6 times its acceleration, which is the unknown. Now let's move on to P. Now we're going to resolve again in the direction of motion, which is left to right. So any forces going straight up or down are not relevant. We don't need to worry about the weight or the normal reaction or anything. Those are perpendicular to the direction we're going in. So the only force in town here, given that there is no friction, is the tension. So again, using F equals ma, our only force is the tension, and that equals 0.8 times the unknown acceleration of A. So we've now got two equations and two unknowns, so we've just got a simultaneous equation to solve. So all I'm doing here is substituting this into here, so the T equals T, so we're just replacing that T there with the 0.8A. So we've got this, and then just following the algebra through, we get the acceleration being 4.2, which was what we were expecting. Now, part B, find the time taken by P to hit the pulley from the instant when P is released. So when will P hit the pulley? Now, you've got to think what's going on here. There's really two parts to P's journey. We've got the part of the journey where it continues to accelerate and is just being pulled along really by Q. So it's going to accelerate all the period of time until Q hits the ground. So it's going to have a period of acceleration. Now, once Q hits the ground, the rope will become floppy. It won't be taut anymore, and it's just going to cruise along. It won't be accelerating anymore. It's just going to cruise along until it hits the pulley. So we've got two periods of time. The first period of time when it's being pulled along by Q, and secondly when it's just cruising with the rope no longer taut until it hits the pulley. So to find out how long that first period of time is, we're just going to focus our efforts on Q and see how long it takes for Q to hit the floor. So what do we know about Q and its journey here? We know that it starts with the speed of 0 before everything's sort of let loose. We know its acceleration until it hits the ground is the 4.2. That's from part A. And we know that the distance it's got to travel is 0.4 meters. So using S equals ut plus half at squared and substituting this in, we can see that the time taken for Q to hit the floor is 0.436 seconds. Now, moving our focus on to P, we're going to need to know what speed it was travelling at when Q hit the floor, because that's going to be the initial speed of our second journey. So what do we know about P? We know that its initial speed was 0. We know that it was accelerating initially when it was being pulled along at 4.2, and we know from up here that this happened for 0.436 seconds. So popping that into V equals U plus AT, we can see that the velocity of P at the second when Q hit the floor is 1.833 ... seconds. So how long did it take for P to hit the pulley for the second part of its journey after Q has hit the floor? Now, as I said earlier on, the key bit to take on board is the acceleration equals 0. So it's going to be travelling at a constant speed. We've just worked out that this constant speed is 1.833 ... The distance that it's got to travel at this constant speed is the 1.5 meters less the 0.4 meters that it's already travelled while being pulled along by Q. So it's going to be travelling at a constant speed for 1.1 meters. Now, What formula do we use? Well, either just go back to the basic speed equals distance over time and rearrange that, or you can just substitute it into s equals ut plus half at squared, but of course there is no acceleration, so that second term is 0. So either way of looking at it, the distance travelled is the speed times the time. So 1.1 equals that constant speed of 1.833 ... times the time. So this second period of time is 1.1 divided by the 1.833 ... giving us this second period of time of 0.6 seconds. So we had the first period of time when it was being pulled along of 0.436 seconds, the second period of time of 0.6 seconds. Adding the two together, we get 1.04 seconds. And then part C, state one limitation of the model that will affect the accuracy of your answer to part A. Well, again, I've just copied and pasted this out of the mark scheme. So examples include that the rope is light, the rope is inextensible, and the pulley is smooth. Question 3. Well, hopefully you find this quite a nice question, because this sort of nicely ties in with all the differentiation and integration you've done in Pure. So here goes. So part A, we're being asked to work out the size, the magnitude of the acceleration of P when P is instantaneously at rest. Now be careful, when is a particle instantaneously at rest? This is when its velocity equals 0, not its acceleration. You know, you can be 0 acceleration and you're still travelling along at 100 miles per hour. I mean, you're not at rest, are you, when your acceleration is 0? So you are at rest when your velocity equals 0. So we've got to solve the equation that we're given being 0. Now I've just chosen to multiply through by -1 just to give me a positive t squared. So I've got this formula here, and it does factorise and gives me these two values for t. Of course, you should use your calculator to speed things up and just substitute in A being 1, B being -4, and C being -12. Well, it gives us these two numbers for t. Now t is time, of course, so clearly -2 is not valid. So we're going to use a time of 6. So we know it's instantaneously at rest after 6 seconds. Now we will need to find the size of the acceleration, not the velocity, the size of the acceleration. So how do we get our acceleration formally? Well, we have to differentiate velocity. dv dt equals a. So differentiating this, we get 4 minus 2t. Substituting in our value of t being 6 that we've just worked out, we get our acceleration being -8. So we're actually decelerating. We've got -8. Now we're being asked for the magnitude, the size of the acceleration, so that's got to be 8 meters per second squared. Now part B, we're being asked to work out the distance travelled by P. So how do we get our distance equation? Well, distance, displacement, is what we get when we integrate velocity. So we're going to integrate the velocity equation between 3 and 0. So integrating this, we get 12t plus 2t squared minus a third t cubed. Remember, you add 1 to the power, then divide by this new power. And then substituting in 3 and 0. Well, substituting 3 into each of these three terms, we get 36 plus 18 minus 9. And we take away from that when we substitute 0 in, which is nothing. So that gives us 45 meters.